مساء الخير. اهلا بكم في السيشن Artificial Intelligence, Robotics, Multimedia and Data Visualization 2. First paper, Charge Time Predictor, a data-driven approach for estimating smartphone charging session duration by Yusuf Awad. 10 minutes, Yusuf.
Hey everyone, how are you? So let's start. So yeah, as the doctor just said, charge time predictor, a data-driven approach for estimating smartphone charging session duration. So this is our agenda. I'm going through introduction, the motivation for this problem, and some background and related work. Then we're going to see the data set that we've used to accomplish this work, the methodology and the experimental results, and conclusion in some future work. So let's jump in. So as we may know that the battery technology, and we can say a general statement like electricity as a fundamental as we know didn't cope up with the fast acceleration and advancement that happens in or still happening in hardware and software, and especially software. We can see like those large language models or small language models, they are hungry for power and they consume lots of power. Even the on-device models, we still need huge amount of power to make them work, which is like kind of bad that nobody like focuses on this problem, that we're trying to prolong the battery lifespan or the longevity of it during the day. Also recently we've seen Apple sacrifice the physical SIM card in their new iPhone Air just to make the battery bigger, not to innovate some new technology that could improve the battery. And also, like the charging process, the way we charge our phone, that we know till this day is hugely one of the main factor that degrades the battery and it reduces its lifespan, which is kind of bad that also the fundamental technologies that we use every day kind of hurt our battery. We're not trying to improve this basic fundamental technology. So enhancing the longevity and overall health of a smartphone battery or any battery in general is an absolute necessity to meet this increasing demand for this hungry power softwares and hardware. So for the background, one of the most well-known protocols to charge your battery is constant current, constant voltage, which means we feed your battery with a constant voltage and current through the charger, and this is the most adopted way in lithium-ion charging process. It hurts the battery a lot as it achieves higher temperature. As when we feed the battery with constant current, the temperature like tend to go higher in a exponential way. And even though it has thermal management system and design, it still failed not to degrade the battery, but just to make it safe. And one example that the thermal system management was a failure, like if we could recall the, I think, Samsung Galaxy S8, which is usually got explode while it was charging, and they had to do a recall and collect all the units from the market. And we know that machine learning algorithm proved that it could predict like the daily repeated task with a high confidence. And as I said earlier, that an intelligent predictive strategy is needed to solve this issue. So jump to the related work. A couple of researchers did some amazing work, but we will see that it's only applicable on Android phone, and it's not touching the fundamental basic layer. So like one of the earliest work was just to create an Android mobile phone and create some sort of physical switch, and you try to put what called target state of a charge, which will the switch get notified from the application and will interrupt the charging process. in simulation, they claimed that they increased the battery lifespan by 1.8, and another research. Okay, we will see that most of the related work only limited in Android, okay, and didn't touch the basic foundational of the charging process, and was tested on simulation, not real world testing. So this is a huge, for me, negative feedback for them. So the data set, we worked on an open source data set. It was collected from 24 students from Rees University from United States. It has all the information we needed, the charging session for these students along the charging session through different intervals, different times of the day, different days, whether work day or a weekend. So we had two methodology when we collected the data. We had to do some feature engineering, and our feature engineering is we calculate the average rate of change of battery capacity that happens during the charging process and the standard deviation, along with it the same for the current that is being fed to the battery. And we also use the workday and the day type, whether a workday or a weekend, because by intuition, if we're charging the phone with a 3 voltage charger, it usually indicates that you are at, you're driving and you're maybe going to work or going to a trip. So to separate this or to make the model understand this, of course, we need something to say, oh, it's a work day, so yeah, the user is going to the work, or it's a weekend, so the user is going in a long trip. So we've split the data into 4 different segments that we're trying to put each user on, which is charging the battery from 0 to 1 hour, like putting your phone on a charger for the maximum 1 hour. The second segment is the 2 hour. The third segment is 3 hours, and the fourth segment is above 3 hours. So we see that we had some battery bias toward the longer charging session, and we had to do some augmentation in order to generate more balanced data set. For the main methodology for our system, we've used an IoT device called Canal Battery Guard, which is I worked on a startup. We invented. I had a sample, but my manager took it from me earlier this day. Wanted to try it, so sadly I can't show it to you now. And this IoT device has some code that sync with an application. In this application, sync with the phone, and it's asked the phone, oh, what you trying to at the beginning of the charging session, trying to calculate the for one straight minute without interrupting the charging process. We try to calculate the as I said, average rate of a charge, standard deviation for the current and the battery capacity, and we try to get the work date. Then we notify this IoT device, okay, here's the plan, how we're going to achieve this charging, and we interrupt the charging processor, meaning that we will try to achieve the maximum amount of battery without in a time frame without hurting the battery. So for our experimental result, for data augmentation, we've used autoencoders. Of course, it's a well-known deep learning architecture. It maps, it is usually of odd number. It has a low dimensional latent space. You take an input, you do it to the latent space, and it generate an output. And we've used this, we've utilized this architecture to generate the augmented data. The most prominent architecture for this type of neural network, we constructed the layers as we see 60, 60, 13, 5, 13, 60 with an epoch of 50. So yeah, this is a picture of the architecture. And yeah, we've seen, and this is the different grid search that we've done, and we've chosen the 5-layer autoencoder with a validation 0.5 because I think when the final when the loss between the validation and training with this period with this limit, it shows us like by the rules of machine learning that you want a smaller value for loss in validation rather than the training. So we took the 5 layers. So yeah, and this is the number of classes that we generated before and after the data augmentation. Now let's jump to the main thing, that the baseline for trying to segment the users. We've used logistic regression as a classification, as a baseline. Then we tried support vector machine, and of course, if you've been developing in between the area of 2020 and 2023 before the LLM, we know that XGBoost back then was the golden algorithm for solving this kind of problem, which is achieved a performance of 0.22 accuracy and F1 score 0.89. And when we try to deploy this algorithm on a real world with 5 users, the accuracy went down, which is kind of bad. And this is also a hint that we're going to see in the future work. So this is a summary of the algorithms and its accuracy and F1 score. And of course, we only deployed the XGBoost as we had a limited amount of resources and costs. So that's why we choose only to try one model, and the one model that achieved the highest accuracy and F1 score was chosen. Okay, so the key achievement, a gradient boosting ML algorithm was successfully used to predict a charging termination session, achieving accuracy of 0.1 and F1 score of 0.87. We've done some okay, like the limitation that still the data that we used was based on one operating system, which is the iOS, the iOS as the 24 student used iPhone. But when we deployed, we made sure that other users, like using Android phones, tried this approach, got succeeded, but still it showed that there will be a difference between the simulation, if you're simulating this process, and between if you are trying it in the real world. Of course, a more sample in the real world is needed, and a more sample in the training phase while constructing the algorithm is needed from variety of different OSs and variety of different flavors of this OSs. As the future work, we propose that focus on a survivor analysis algorithm, which is a well-known type of algorithm known for the prediction of a churn of a process, but it will need more data, so more data should be collected. And also, okay, expanding to a larger user base, as I said earlier. So yeah, and that's it.
شكرا يا يوسف على البرزنتيشن. في أسئلة من الحضور؟ السلايد ده تقريبا أنت حطيت فيه عدد من الإكسبيرمنتس فيها أكتر من لاير.
Okay, this one.
لا كان في تيبل كده.
It's back.
أيوه. هنا انت ممكن تقول لي انت جربت 3 لاير و5 و7 و9، ايه تصورك لاختيار الارقام دي لعدد اللايرز؟ وهل ما بتعتبرش 9 دي رقم كبير؟
Usually I've used grid search, an algorithm with a limit of 3 and optimal of, I think, maximum of an odd number of 15, but due to the budget.
يعني السؤال، هل انت اخترت الكلام ده بيزد على تصورك؟ ولا في حاجه معينه خلتنا نستخدم الارقام دي لللايرز الموجوده؟
No, we try different tests. Yeah, that's basically of a grid search. You're trying to achieve you search along a space and you try to achieve the best accuracy.
طيب ممكن تقول لي اختصار للترايلز دي طلعت منها هل عدد اللايرز ده فرق في ايه معاك؟
Yep, of course. Like 3 layers, it is accepted because of between the loss between the training and validation. We want the loss in the training and the validation, like the training in the training loss should be bigger than the validation, which is give us an indication that the model will perform somehow good. But still, 5 layers way better because the difference got way bigger. And for the 7th and then the 9th layer, we've seen that for the 7th layer, it's as I'm saying, it is a close fit, so potential overfitting may happen, and for the 7th layer, a potential underfitting may happen. So that's why we excluded the 7th and the 9th layer, and we've
شكرا يا يوسف.
طيب, I don't have questions, but I have a quick comment.
Okay.
When going to real-time deployment, it's expected that the results will go lower.
Yep.
Because you mentioned إنه دي it's a down effect or it's مش فاكرة قلت إيه بالظبط يعني.
Yeah, it is a downside. Some people try to in industry we try to do simulation, and after the testing and simulation we do some kind of equation that will reflect on the real world.
It is expected.
Yep, but
this is how it works.
It is expected.
أنت في controlled environment في ال scenarios whatever you run the simulation on, and then when you go for a real-time deployment or a real-world deployment, you should expect that numbers would be lower. But actually, the numbers are not that low. Yeah. The difference is not that big. It's
because people tends to have the same charging
exactly. It's an accomplishment for your paper rather than a downside.
It is kind of like it's still kind of
having a close range between the real time and the simulation, or the real world and the simulation, is a good point.
It is a good, but still we can achieve way better if we collected a more real world data.
That's just my comment. Yeah. Thank you.
Thank you.
شكرا يا يوسف.
Thank you.
Our second paper is depression detection in speech using generative models by Lujain Amar from the GOC.
Okay, so hello everyone. I'm Lujain, and today I'll be presenting to you my topic titled Depression Detection in Speech using generative models. Okay, so these are the things that we will tackle today. Let's start by the introduction. Okay, so do you know who these two people are? This is Serena Williams and this is Michael Phillips, two pro players who suffered from depression. Did you also know that almost 280 million people around the world suffer from depression? This is because traditional depression detection is extremely time-consuming and not always accessible, making people undiagnosed and risking their lives. Also, some people avoid getting treatment. This is because of the stigma around the mental health and how society judges people. Moreover, to this day, because of medical data privacy, depression-related speech data remains scarce. So, as a developer, having limited availability of depression-related speech makes it a bit challenging to train my model and achieve high model accuracy. Also, it's a bit difficult to generate high-quality synthetic speech and accurately evaluate it. So these are some of the papers that I've read. All of them use the same data set, which is the diagnosed data set, as you can see here. And also, they had common limitations, which is the small data set size, and more importantly, the data imbalance. So my objectives would be utilizing generative models to generate depressed speech data, then developing a machine learning algorithm to detect depression in speech, then analyzing the impact of different feature extraction techniques, and lastly, evaluating the generated synthetic speech and the results of my model. So what if your voice could reveal more than just words, and by using AI, we can help save more lives? Let's find out in my methodology.
معلش لو ممكن تبعدي بس المايك شوية عن البيت شوية عشان القاعة أصلا عدد صغير. شكرا.
Okay. So a quick overview is that I want to detect depression in speech by analyzing the acoustic features, meaning the tone, the pitch, and the jitter, which is how your voice sounds rather than what's being said. Also, I'll be using the generated synthetic speech to address the data scarcity part and to try and balance my data set a bit more. So let's start by the synthetic speech generation part. I've taken the transcriptions of the eDAG dataset and I'll be telling you more about it later. Then I converted these original transcriptions using the Gemini Flash 2.0 model into newly paraphrased transcription. And then I converted them into audio files using the Koki text-to-speech model. So let me play a speech sample of how the synthetic speech sounds.
More like numb, just trying to keep moving and stay healthy, I guess. Lately, nothing seems to bring me joy. Being active and healthy outdoors feels impossible. Activities like hiking, biking, rollerblading, and skateboarding used to bring me joy. But now they just feel empty.
Moving on to my overall project plan, as you can see, I have two main inputs. The first one, which is the generated synthetic speech, and the second one, which is my main input audio data. So I requested this data set from University of Southern California. It's called the eDAG dataset because it's the extended version of the DICOS dataset that was used by previous papers. And as you can see, there's a huge data imbalance, which is not good to train my model. And also let me play a speech sample to see how the real audio sounds like.
It's very difficult to make it here in Los Angeles. Business and computer graphics. I'm not working in it right now.
Okay, so this is now my dataset after augmenting it with the generated synthetic speech. And as you can see, the dataset has a better balance than before the augmentation. Then after that comes the pre-processing state, which I remove the silent parts that you've listened to in the last audio file and things that could distract my model while training it. And let me also play the same audio file after the pre-processing.
It's very difficult to make it here in Los Angeles. Business and computer graphics. I'm not working in it right now. I'm working in retail.
Okay, so after that comes the feature extraction phase and a part of it which is the segmentation. So I've made a 4-second segmentation for the depressed participants and then a 12-second segmentation for the non-depressed participants as an attempt to create more training samples of the depressed participants and to try and create more class balance. Then I've done the frequency-based feature extraction where I've extracted 15 feature from each segment, 1 spectral centroid, 1 zero crossing rate, and 13 MFCCs. And then I use the same split provided in the dataset, which is 60% training, 20% development, and 20% testing. However, I wanted to experiment more. So I've done a second experiment where I've used Wave2Vec. And let me tell you about it first. It's a deep learning model used for audio feature extraction and automatic speech recognition. And I've used the base version of it in my second experiment. So for the segmentation, I've done a 10-second segments for all participants. However, this was used only for memory management. Then I've used Wave2Vec 2.0 to make statistical feature extraction for each segment. Then I returned a 4-dimensional vector for the whole audio file. And then I've used the split provided by the scikit-learn train test split where I've used 70% training, 20% testing, and 10% development. Moving on to the machine learning model. But let me tell you first why I used machine learning instead of deep learning. It's because deep learning requires huge amounts of data. However, this wasn't the case in my project. So traditional machine learning models proposed a better solution, and also they have lower computational costs. So for experiment 1, I've used support vector machine, random forest, and logistic regression, and the model is classified each segment individually, then made majority voting in order to identify the final participant table. For the second experiment, I've used the same 3 models in addition to XGBoost, and then the model made participant level classification right away. Then I've used the traditional evaluation metrics to evaluate the performance of my model. Then for the synthetic speech evaluation, I've used the FAT score, which is the quantitative metric used to evaluate the quality of the generated speech by comparing it to real audio. Then I've done another evaluation for the synthetic speech, which is human in the loop, which is using humans' feedback to evaluate the quality of the generated speech. So it's a qualitative metric, and I've done it using Google Forms. Let's take a look at my results. So I've done 2 versions for each experiment. The baseline, which is the first version, I trained and tested my model using only real data. Then for the second version, I trained my model using the real plus synthetic data. Then I tested it using the real data only. And as you can see, in the 2 experiments, from version 1 to version 2, all of the scores actually improved. So this means when I augmented my data set, the results improved. For the fast score, having a lower score closer to 0 means that the quality of the generated speech is better. And I had a 9.2 score, meaning that the quality of the generated speech was good. However, there were some differences from the real audio. For the human in the loop evaluation, the first question was asking about how natural does this audio sound. And as you can see, almost the whole scale has the same score, except for number 4, which is leaning more towards the not natural part, which backs up the fat score, meaning that some humans were able to identify these differences in the synthetic audio file. Then this is asking about the clarity, almost 70% leaning towards the very clear. Then this is asking about how well does the audio file convey emotions. The graph looks almost symmetrical. However, if we look closely, we'll find that the strong emotions part is bigger than the no emotions part. Then the last question was asking the participant to evaluate the speech sample as real or synthetic, and participants accurately evaluated real speech samples by 70%, and also the synthetic speech samples by the same 70%. To conclude, I think synthetic speech data has the potential to improve the model's performance. However, its effectiveness is highly dependent on the model and the quality of the generated synthetic speech, but it actually presents a practical and a scalable solution for domains where data privacy is a concern, like the medical domain. Lastly, depression could really be detected from acoustic features only, offering a non-invasive and a practical approach for detection. For the future work, I think we can experiment with multiple data sets and languages, as we're only analyzing the acoustic features, so language won't be a barrier anymore. We can also improve the realism and generalization of the synthetic speech data. Then we can experiment with deep learning architectures and explore other data imbalance handling techniques. Lastly, we can apply this framework to real-world applications like mental health monitoring for athletes, early intervention tools for schools, and lastly, chatbots that identify depressive tendencies. So this is my vision, for people to be able to talk to a system and for it to identify the depressive tendencies. So lastly, my goal is having faster, easier, and more accessible depression detection for everyone. Thank you. Any questions?
Thank you, Jenny, for the presentation. Do you have any questions on the floor? So I have a question for you. You generated the synthetic data using Gemini Flash 2 version 2, right? So do you expect if you use another AI model that will affect your data, affect your model, the whole system?
Okay, so I didn't only generate the synthetic data using the Gemini 2.0 model. I first paraphrased the transcriptions using this model, and then I converted the text to speech using the Koki model. And my answer to your question is yes, maybe using different models might affect the quality of the generated speech. That's why I put it in the future work to improve the generalization of the synthetic data, because I think it would affect.
عندي سؤال بالنسبة لعدد السامبلز اللي انت استخدمتيها، يعني ازاي اعتبرتيها sufficient بالنسبة لك؟ ليه الرقم ده تحديدا؟ ولما جيتي تقارني مع البيبر الأخرى في related work ذكرتي ان السامبلز كانت سمول نمبر، بس ما قلتيش هي يعني في رينج كام او ريلاتيف تو الرقم اللي انت عملتي له جنريت، هي تعتبر نسبه كام؟ فالاجابه
Okay, ماشي. We can partition your question into smaller parts. The first part, you were asking about the number of the samples. My data set is called the extended DICOS. So it's the bigger version of the data set compared to the DICOS only that was used in the previous papers. So the DICOS contained 189 samples. However, the extended DICOS, I had a diagram in my presentation which contained, yeah. Okay, so here the extended DIC dataset, which is the one on the right, has 274 audio files in total, 66 only depressed, and the rest are not depressed. And then I almost doubled the number of the depressed participants when I generated the synthetic speech, which made me have a total of 130 audio files. Okay. Okay, so as I mentioned, I've taken the transcriptions of the audio files. So I had 66 transcriptions for 66 patients. I paraphrased these transcriptions in order to retain the meaning, in order to be able to use the same labels. So that's why I have 64 only. 2 audio files were corrupted while generating. So that's why I only doubled it. And then if I wanted to triple it, I had to paraphrase it again. However, there was a risk of overfitting, where while I was paraphrasing the transcription, there wouldn't be a major difference. That's why I only doubled it.
I have a follow-up question on the dataset as well. We can discuss later one-to-one if you want. But you mentioned in your introduction that it's not what's said, but how the tone, the voice, and the way things are said where you detect depression, right?
Can you paraphrase?
So it's not about what the person is saying that you're analyzing, it's about how they're saying it. So why rephrase?
Okay, you're correct. I'm only analyzing the acoustic features, so the linguistic part I don't care about. I paraphrased it because I couldn't only generate audio files straight away using a text-to-speech model or a speech-to-speech, because I wouldn't be able to determine if the audio file that was generated using an LLM was depressed or not. That's why I used the transcriptions. I still don't care about the meaning. I only used it in order to be able to generate other speech samples.
And you clone the original sounds, you mean? Or just rephrase the text and then generate audio based on that text? Do you know what I mean? How did you preserve the original way of saying the sentences, whatever they are?
Okay, so I first, the part you said cloning, I didn't clone the voices of the participants in the original data set. I generated only 2 audio files, purely generated new text and new audio files using a tool called 11 Labs. And then I went back to a therapist to make sure that the generated speech was okay to use and it had the depressive tendencies in the speech. Then using these 2 voices that I newly generated, yes, to generate the 64 new audio files.
Thank you.
Did I answer your question? Thank you so much.
Rajai?
Abdel Basit. Our next presentation, accuracy enhancement of Arabic handwritten signature verification, a case study of mobile net, V2.
Ayo. Okay. Shall I start? Okay. Hello, everyone, and welcome to the presentation. My presentation today. I am Anis Ismail, and I'm today presenting the work of Aisha Al-Rozeki. This work is supervised by Dr. Abdel Basit and myself. And basically, so this is the outline of my presentation. I will introduce an abstract of the paper, and then an introduction and how we collected the data and built the model, and finally we did evaluate the model. So the main issue we are trying to solve here is how to detect if a signature is fake or not. And this is already done in many publications before, but in English signatures, there are few studies about Arabic signature verification. So the main objective of this paper is to recognize handwritten signatures using mobile net version 2 model. And so we collected a data set of offline Arabic signatures. And then we applied the models on this data set as well as a reference data set, which is the CDAR data set. Okay. And we achieved high accuracy, about 99%, and very high precision, I recall, and I don't remember the numbers. I will show them at the end. Okay. So let me introduce the problem we are trying to solve. Now you sign your signature, and we would like to verify automatically if this signature is your signature or is it a forgery. And in general, there are two types of signatures, offline and online signatures. So an offline signature is where you sign on a paper, and then we take this signature after you finish the signature, and we try to verify or check the authenticity of this signature. While an online signature is actually, the checking is done while you are signing. And this is used in banks, for example, where you are signing on a tablet or some electronic device. It captures a step-by-step your signature and the trajectory of the signature you are making. But actually, we are not we are not dealing with online signatures. We are just focusing on offline signatures. Okay. So we are given a set of signatures, and we would like to build a classifier to detect if a signature is authentic or forged. And we used different deep learning models to test our system. Okay. So in this paper, we used the mobile net version 2, but in other studies, we actually used different models and compared the results. Okay. So the basic idea is that we need to collect some data signatures. The Arabic signatures data set is not available. Some publications use an Arabic signature data set, but they are not publicly available. I tried to contact the authors, but the data set were not to be shared. So, and then we selected some models, and we built the models and trained it. And at the end, we had a classifier to tell us if the signature is original or authentic, or if it's a forgery. Okay. So we actually asked about 150 individuals for their signatures, and only 95 responded. And from those that we collected, only 40 of them were not valid, and we ended up having about 55 individuals, and each one of them they made their signatures 24 times. So in total, we are having about, or actually 1,320 signatures. And then for each of those 55 individuals, we got their signature and show it to some people, and we asked those people to try and replicate their signature or forge this signature. So we could have a data set for forged signatures. and we scanned the signatures using 300 dpi resolution, because the different resolutions actually affected our model and affected the accuracy and the training time of the model. So this is the form that we use to distribute, and we ask the person to write their signatures on different days, at different times of the day, but the same name. Because one issue we faced is that people used different signatures. Okay, so we just innovate and make new signatures. So for example, this is one sample of the data that we collected. So as I mentioned at the beginning, we tested the models on two data sets. The CDAR data set, which is the benchmarking data set. This is a data set available online. And our Arabic data set, this is the one we collected, and we tried at least to get the same number of signatures as their own data set. And we tested on CDAR, so that actually to verify that the models and the fine tuning that we did on the models is actually working, and it is not just overfitted on our data. So we tested it on the benchmarking data, and we also combined the two data sets together and ran the same model on the combined data set, and it was also had high accuracy for predicting authentic versus forged signatures. Okay, so some data pre-processing. We scanned the data set, as I mentioned, 300 dpi in grayscale. We removed white spaces around the name and removed a lot of noise. And we also converted this into a black and white image. All of this actually reducing the size of the image, which basically reducing the input of the neural network. And this actually had a lot of effect on the accuracy and the training time of the model. So some challenges we faced is that actually large image files take too much time to train. So we had to reduce that while actually not getting rid of some important features. So this was a challenge. We tried different sizes and different bit width for the image files. Also, we tried different resolutions. At the beginning, we started with very high resolution, which is 1200 dpi, but this was too much, and it gave us a lot of errors because actually it contained a lot of noise. So very high resolution actually picks up some artifacts that are not part of the signature. Also, we noticed that after reviewing the data and at the beginning we had got a lot of low accuracy results. So when we investigated, we found out that a lot of people just wrote different signatures. For example, the same name but different signatures. So they will just innovate, not using one signature. And also one issue is that we had to crop about 480 signatures manually to actually crop the image to just get rid of some of the white noises, because people didn't. So for example, as you can see here, yes, so this box is the pointer. Yes, so as you see this box, you are supposed to write the name or the signature inside the box, but some people wrote it at the corner or at the bottom, and maybe in some cases crossing the border, and these cases were actually removed. Okay. Yes, so we did the normal data splitting, and we also did a cross validation to test our model. So in this paper, we used the mobile net v2 model, which is used as a transfer learning model. So basically a transfer learning is when you have a model that is already trained for images in general, but then we actually want to use it to classify specific type of images, for example. So what we do is that we take the same network, remove the final layers, and fix the first layers, and freeze the weights, and then retrain only the final part of the model. So it is actually learning the new features of this task. Okay, so I will not go into details because of the time. This is the...
Can we just make sure we're in time? We have like less than 1 minute.
Okay,
Thank
so
you.
yes. So what we did here is that we tested the model, the accuracy was very high, about 98%, and the precision and recall were also so we had the precision for 1% for one, and the recall for 96%. Yes, and this is when we use the cross validation, and in some of the cases when we did the validation, the cross validation, some of the cases had good results, but on average the total was actually good, as you can see in the numbers here. And this is a recap of the results that we achieved. Yes, so to conclude, we used a deep learning model, namely convolutional neural networks, to detect signature verification. We had high scores, accuracy results, about 98.5. And we did a lot of data pre-processing and augmentation to actually train the model. And we evaluated the model using all the known metrics, but I didn't include everything in this presentation. So future work is actually to do a similar approach, but on online Arabic signature. It will use actually different technique, so the technique would be different. Another future work, which is very common in a lot of similar papers, is actually to handle left-handed individuals. Apparently, their signature is different if you're using your left hand, and the systems trained on right-hand signatures do not have a high accuracy on left-hand signatures. So that's it, and thank you for your attention. And if you have any questions.
Thank you for your presentation.
Thank you.
Do we have any questions? So I'll ask you a question.
Yes.
Early in your slides, you show us architecture or something like boxes. One of them was model selection, but I only saw that you are using MobileNet version 2. So
Yes.
did you on what basis did you choose it, or did you do other experiments?
Okay, we actually used multiple models, but for this paper we only submitted one model, and another model was actually in another paper. So we used at least 3 models, but the highest result was the VG16 model. This one it almost got 99%. This one got 98.5, but the results were very comparable. But the advantage of MobileNet V2 is actually it's very lightweight model, so it could be used on a mobile phone. It doesn't need a lot of computation.
Thank you.
Thank you.
عندي سؤال
اتفضل.
بالنسبه لان الهاند ريتن او الريكوجنيشن بتاع الهاند ريتن قتل بحث. انت شايف الريل كونتريبيوشن بتاعك في البيبر دي ايه؟
المين كونتريبيوشن اكشلي الداتا كولكشن، يعني الداتا سيت بالعربي مش متاحه اونلاين. هو لحد دلوقتي الداتا سيت بتاعتنا برضك ستيل واز نوت.
يعني تقصد ان الجزء من الكونتريبيوشن بتاعك هو بيلدينج الداتا سيت حضرتك؟
Yes. It actually took a lot of time and effort just building the data set, and a lot of the papers using Arabic signatures, they use their own data set and they do not share with anyone.
وانت اكتفيت بالداتا سيت اللي انت عملت لها تجميع، صح كده؟
نعم.
الداتا سيت اللي انت ذكرتها ان انت بنيتها هي دي الوحيده اللي انت اشتغلت عليها؟
لا، والسيدار.
السيدار دي بقى في بيبر ثانيه اشتغلت عليها
كتير. في بيبرز كتير.
طيب فين الكومباريزن او الكومباريتيف اناليسيس بتاع شغلك مع شغلهم؟
انا ما قارنتش شغلي بشغلهم ان انا بقول ان انا بعمل حاجه احسن على سيدار. انا المين كونتريبيوشن بتاعي ان انا التكنيكس، اولا كولكشن الداتا سيت كولكشن، ثاني حاجه ان التكنيكس ديت اللي اشتغلت مع الداتا سيتس اللي بالانجلش اشتغلت مع الداتا سيت اللي بالعربي. انما انا قارنت مع سيدار علشان اتاكد ان المودلز اللي انا بنيتها بتشتغل صح على حاجه اوريدي معروف انها، يعني ده البنش مارك. فانا عشان اتست الموديل بتاعي، لان انا لو عملت الموديل بتاعي على العربي بس ممكن يبقى فيه اوفر فيتنج ان هو شغال على الداتا دي فقط. انما انا عملت له تيستنج على داتا سيت اوريدي معروف ان في اكيوريسيز وريزلتس كويسه بتطلع بالنسبه لها.
دي في حد ذاتها مقارنه، هي فين؟ يعني انت قارنت على السيدار علشان تشوف ان الموديل بتاعك شغال اوكي ولا لا؟
حلو.
عرفت ازاي انه شغال اوكي؟
ما طلع الاكيوريسي عاليه، ما انا وريتها. يعني انا طلعت، ما قارنتش انا البرفورمانس بتاعي بالبرفورمانس بتاع البيبرز الثانيه، بس انا قارنت البرفورمانس بتاع الموديل بتاعي على سيدار، لقيته طلع ريزلتس كويسه 98% تقريبا. فعرفت ان الموديل بتاعي مش بس شغال على الداتا سيت بتاعتي، لا يقدر يشتغل على داتا سيتس اكتر. يعني انا كنت بتاكد بس ان الموديل بتاعي شغال صح. شكرا لحضرتك.
Our next presentation is by Safe, right? Okay, is Safe here? Okay. Real-time cognitive emotion mapping for human avatar interaction in VR.
Good afternoon, everyone. My name is Saif Sheikh, and today I'll be presenting my topic, real-time cognitive emotion mapping for human avatar interaction in VR. And there is a quick overview of today's presentation. Now let's start by the introduction. Our work started by one question: what if technology could actually understand emotions? From here, we aimed to create a culturally authentic Egyptian avatar that can express both facial and vocal emotions, aiming to improve engagement and emotional connection for children with communication disorder in educational field. But we faced two major problems. One was that many avatars created looked too robotic, and the other one was that there are almost no avatars represented Egyptian culture. We tried to make our own avatar, and we tried two methods. One was deep fake masking, but we couldn't find a realistic base avatar to start with. And another one was motion capturing, but we lacked access and resources to full body suits and professional studios. And here is an example for both methods we tried. And now let's talk of some of the previous works that influenced my work. The first paper showed how children with communication disorder responded positively to virtual tutors. The second paper, EC Avatar, influenced my work with the use of blend shapes and different intensity levels for each emotion. And the final paper showed also how children with communication disorders reacted positively for emotionally expressive avatars. And now let's start. Let's show how the system was built. This is a block diagram of the initial workflow. We started with the dataset collection. In the dataset collection, we started by choosing an actor who represents actually Egyptian culture, which was Ahmed Helmi, and we started downloading his movies, extracting clips from his movies, and labeling each clip with one of the 6 core emotions: happy, fear, sad, angry, surprise, and neutral. Then this data was passed to the next step, which is pre-processing. In pre-processing, we used two main frameworks, OpenCV and MediaPipe. OpenCV was used to split clips into frames. MediaPipe was used to extract 468 facial landmarks and 33 body landmarks, and then we also extracted spectrograms from the speech data. This data was then used to build 3 emotion recognition models, which are facial, body language, and speech. They were all trained using ADAP optimization after the dataset was divided into 80% training and 20% testing. Facial model needed the face crops to be resized into 224 multiplied by 224 pixels to be compatible to the input. Finally, a weighted emotion prediction was done using the 3 models. However, the models didn't achieve enough accuracy that we needed, so we shifted our focus into another direction. And this is a new block diagram for the workflow. We also started with the dataset collection, which didn't change, and then we moved to the avatar design. In the avatar design process, we started by an avatar that was downloaded from Unity Asset Store that initially had 7 blend shapes. 7 blend shapes were not enough to convey the wide range of emotions we wanted, so I imported the avatar into Blender and created 10 more blend shapes using some tools like Smooth and Elastic Deform and Grab. Here is an example of the process itself while creating the 10 more blend shapes. And then we go to the next step, which is emotion matching. In emotion matching, we took 90 samples from the dataset collected, 90 face crops, 15 for each emotion, and then we categorized each of the 15 emotions, the 15 face crops into 3 different intensity levels. except for surprise and neutral, only had one intensity level. Then we matched each face crop to the avatar by changing the blend shape weights. This is the step where we matched the avatar to the face crop. We took average of the blend shape weights, and these are our aesthetic emotions in the end. We had final 14 emotions that we used. Then we go to the story creation and labeling process. In this step, our theme of the project was an educational storytelling avatar. So we started by choosing some topics that actually has emotional content, and manually created these stories and labeled each sentence in the story with an emotion and intensity to then be passed to the audio generator. And now in the audio generation step, we used the text-to-speech model that was found on 11 labs, and each sentence was passed to the text-to-speech model while manipulating some variables and parameters to match the sentence emotion. Then we downloaded the final audio generated to be an input for the avatar. And then we wanted to add some final functions, so we added 3 features. A blinking system that happens every 5 seconds to avoid robotic look, jaw movement while talking using RMS values, and a smooth transition between emotions using linear interpolation to make the transition between emotions look more natural. Then we had our final avatar, but before deployment, we wanted to see how actually the avatar engage with the users. So we designed 2 user studies. The first one was avatar engagement questionnaire. 40 participants were shown 3 videos of the avatar with emotions and 3 videos without, so we can see how emotions made the engagement different. The other one was an emotion recognition quiz where participants were shown all of the 14 emotions and asked to identify each one. And now, here are the results. These are the results of the recognition models. As you can see, facial emotion recognition model achieved 58%, speech achieved only 55%, body language only achieved 30%. And due to their low performance, we decided they are not ready for the final implementation, and that's why we shifted our focus into the other direction. Here is a sample of one emotion with the 3 different intensities. And now I will leave you with a demo video of how the avatar works.
في فصل مزدحم في مدرسة حكومية، كان آدم طفل عنده توحد، قاعد في آخر الصف وعينيه دايما على الحيطة. كان بيحب الألوان والأرقام، لكن صوته قليل وكلامه مش دايما مفهوم. أول مرة أتكلم في الفصل قاطع المدرس بحماس وقال رقم مش له علاقة بالدرس. ضحك الطلاب والعيون كلها بصت له باستغراب. آدم سكت وبطل يحاول يشارك. بس المدرسة الجديدة كانت مختلفة، قربت منه وسألته بهدوء: تحب تشرح لي اللي في دماغك؟ عيونه لمعت ورسم على الورقة أكثر من مقطع، ومن يومها بكى في ركن صغير في الفصل اسمه زاوية آدم يشرح فيها بطريقته.
Here you notice how the avatar blinks every 5 seconds and the jaw movement according to the loudness of the audio, and also the transition between emotions. And here, some of the responses of the main questions of my questionnaire. First question was, which version did you prefer overall? An overwhelming 95% said that they preferred the version with emotions. Then we asked, would you prefer avatars with emotion in future educational or storytelling videos? Also 95% said yes. Then we asked, do you think facial expressions make avatars more believable? Again, 95% said yes. And the final important question in this questionnaire was, do you think as a child such an avatar could have made learning more fun? 82.5% said yes, which is a huge number of participants. This was the emotion recognition quiz results. Out of 25 responses, 22 actually achieved full score, and only 3 achieved 12 out of 14, which is also a high score. To conclude, this project successfully achieved its goal as a proof of concept that developing an avatar speaking Egyptian Arabic and showing facial emotions and vocal emotions can actually be used in future educational field. And the emotions were created using real actor samples and implemented through blend shape tuning in Unity. Also, the user study with 40 participants showed that 95% preferred the emotional avatar, highlighting how the emotions for the avatar affected the engagement and realism of the avatar. And this opened the door for future development. For future work, I wanted to work on 2 things. The first one was that I wanted the system to be more dynamic and personalized. So I wanted to enable the system to take a photo of the user, detect the shown emotion, and have a chatbot generate a story that matches this emotional state. This creates a more personalized and dynamic plan. Then I wanted to redesign the avatar to have a more Egyptian appearance, and this will make it feel more culturally familiar and visually authentic for local users. And this will thank you.
Thank you, sir. So do we have questions from the floor? I have a comment or question for you, sir. You told us that you choose Ahmed Helmi as an Egyptian face, but I don't know why do you need to know this? Because it's not related to the avatar anyway. The avatar, we don't know the personality was created. You used to create the avatar, right? So if it is Ahmed Helmi or not Ahmed Helmi, it won't affect the avatar or affect the creation of the avatar, right? So there is no relation between Ahmed Helmi and the avatar, especially have a female avatar and a female voice and فصحى Arabic, not Egyptian Arabic.
مالهاش اي علاقه، بس هو انا وانا بجمع الداتا سيت الاول كنت محتاج ان انا اجمع فيديوهات كتير لحد مصري بيتكلم عشان اخد الايموشنز منه، او اخد مثلا لو هو زعلان اخد شكل وشه منه. فهو يعني المنطقي ساعتها ان انا مثلا مش هعرف اخد فيديوهات لنفسي، لان انا مش هعرف اجمع فيديوهات كتير. بس واحد زي احمد حلمي هو عنده افلام كتير بكواليتي عاليه واكيد فيها ايموشنز كتير، فساعتها الموضوع كان هيبقى اسهل ان انا اجمع الفيديوهات دي.
Again, I don't get what does the Egyptian personality do affect the avatar creation. You need the sad avatar, it's sad face, Egyptian or American or British or any nationality will have a sad face, right? Happy face.
ايوه انا فاهم، بس يعني
yeah, there is a difference between Egyptian happy face and English happy face.
لا هو ساعتها في الاول خالص كان المفروض ان يكون في امبلمنتيشن لبادي لانجوج، وساعتها بادي لانجوج كده كانت هتختلف من كلتشر لكلتشر. وفي نفس الوقت يعني انا ساعتها خدت الداتا سيت كولكشن دي، انا كنت هحتاجها لو انا هعمل فيوتشر ورك او كده، فانا كده محتاجها.
So you need to create a full avatar, not just the face.
بس هو ده يعني ما اتعملش دلوقتي، هو مش امبلمنتد دلوقتي.
Okay, thank you.
Thank you for sticking to your time. Bravo. I just have a quick comment / question on the questionnaire. البارتيسيبنتس دول كانوا ايه الباك جراوند، ديموغرافيكس عامله ازاي يعني؟
كان في عادي، هو كان حاجه راندوم.
okay.
كان الايدج عادي في ناس كبيره، وكان في ناس شباب عادي قدي، ويعني كان في ناس برضو اعرفها وناس لا.
okay. It's worth mentioning في اي questionnaire عشان يبقى statistically بس significant. هي دي قصه كبيره يعني، بس to sum up انت بس كنت محتاج تقول لنا الباك جراوند بتاع الناس دي عشان نبقى فاهمين الريزلتس بتاعتهم biased مش biased randomly sampled لا كده يعني.
تمام.
Thank you and thanks again for time bro.
Our next presentation is detection of large language model generated text, comprehensive review by Dua Mustafa.
Hello. This presentation is a comprehensive review of large language model generated text detection. It covers the necessity of detection, difference between human written and large language model generated, and various detection framework will approach key challenges in current detection approaches, plus in future directions. Advanced large language model such as GPT-4, GPT-5, Gemini include now produce text that is virtually indistinguishable from human written. This capability offers additional benefits across many tasks, include answering questions, scientific writing, drafting mail, code generation, but also introduce significant concerns, such as the rapid spread of misinformation, academic cheating, fake news, fake reviews. As a leader, the ability to effectively detect large language model generated content has become an essential task for ensuring responsible AI usage. Difference between human written and AI text or large language model generated text. Human written text tend to be more creative, unique, variable sentence structure, contain minor grammatical error, critical thinking applied. But large language model generated texts have repetitive and more uniform sentence structure, tend to be objective, natural, grammatical, perfect, error-free. They produce inaccurate data. Detection framework, white box detection, the detector has full access to the model. But while black box detection, the detector can access to the model only by API. Current detection approaches such as watermarking-based detection, feature-based detection, neural-based detection, and human-assisted analysis. Watermarking-based detection, a mechanism working by embed hidden signals into text during or after text generation. Feature-based detection, working by focus on stylistic feature, statistical feature, semantic features. Neural-based detection is using transformer model to classify text AI or human. Human-assisted analysis, working by augment on human expertise and analytical skills to analyze the text, analysis logical error, and massing human touch or emotional depth. This is rating a comparison between current detection approaches based on their approach. First, in watermarking approach, there are different techniques. The difference between these techniques, some techniques working by embedding signal into token level, and other techniques working by embedding signals to semantic embedding. Feature-based approach, some techniques working by control a focus on token level probability, and other techniques working by generated many versions and computer similarity between different version and the original text. Neural-based approach techniques in neural-based approach working by using transformer model or neural-based approach. Some writing hybrid approaches such as BDD, LM, and the GBM combine different techniques. The key challenges in current detection approach, robustness against perturbations. Many detection approaches are sensitive to paraphrasing, sensitive to replacing synonyms, generalization across domain and the model. Detectors struggle to generalize across domain or across models. Model access dependency. Detection approaches such as watermarking detection approach require the full access to the model. Rapid advancements of large language model, newer model, or advanced models such as GPT-4 and Claude 3 produce tickets that is more coherent, diverse, and human-like detection. Lack of interpretability. Some writing detection approach such as a neural-based approach as a black box, providing binary output without explaining the reasoning which makes the results. Scalability and the computational costs. Many exciting detectors require substantial computational resource, especially in neural-based and feature-based approach. Text length sensitivity. Some detectors working are often optimized for narrow range and show poor performance outside this range. Data scarcity. There is a limited high-quality label dataset. Key evaluation measures used in large language model generated text detection: accuracy, the proportion of correctly classified text samples, how many texts predicted as AI, recall or true positive rate or sensitivity, the proportion of AI generated text correctly detected. The F1 score is a harmonic mean of precision and recall. False positive rate, the proportion of how many of human written text incorrectly classified as AI. The AURC added the model capability to differentiate between human and AI under various thresholds. Future area, building or developing hybrid approaches that combine different feature types such as semantic, statistical, enhanced robustness, train the approach to work on paraphrasing text, improve the generalization, evaluate that approach to work in multiple domain and multiple model, continuous update, test and train the proposed approach with data generated from new or advanced model.
Thank you, Dua. Do you have any questions?
Thank you for your presentation and for sticking to the time. What would be your recommendations? I understand that this is a survey paper. So what do you see as next steps for research in that domain?
Building a proposed approach that can detect large language model generated text from advanced models.
So you want to focus on the detection of LLM generated text, right?
Yeah.
Thank you.
شكرا للالتزام بالوقت. شكرا.
Our last paper for this session, machine learning models for predicting deformation in RC slabs shielded by auxetic sandwich panel under impact by Behi El-Genzi, right?
Greetings, everybody. I'm glad and pleased to be presenting in front of everybody and the committee panel. So our study is very unique, titled Machine Learning Models for Predicting Deformation in RC Slabs Shielded by Auxetic Sandwich Panels Under Impact. My great co-authors are Dr. Al Hussain, who is my supervisor, whom I'm grateful to be her student. Also a skillful researcher, Zahi Yusuf Al-Gandi, and myself, Zahi Yusuf Al-Gandi. So we are going to be introducing our topic and understanding the context behind it and how we were able to generate the data set through numerical modeling. Then we are going towards explaining the machine learning framework implemented and discussing the results, coming out with conclusions and outlooks. So starting with the introduction, why is our study unique? Our study is unique because it showcases an AI application in interdisciplinary field, combining civil engineering as well as mechanical engineering or materials engineering. Our context here is we are talking about a protective system consisting of an RC slab with an auxetic sandwich panel above it, as you can be seen on the right here. And such system with these two components are called sacrificial cladding system, which has many applications in defense, transportation, or industrial facilities sector. So our main aim here is to be able to predict the deformation or the damage that could occur on the sandwich panel and how much such damage could be transferred to the RC slab beneath it. So our aim is for the sandwich panel to resist most of the damage occurring to our system. These systems can be seen in defense places and where protection is necessary from attacks or impacts or blasts. So the typical the typical way of analyzing such systems would be using finite element analysis softwares such as ANSYS or Abacus in order to be able to know how much damage or deformation that occurs in the system, which is able to predict such deformation with great accuracy. The problem is that such softwares are computationally expensive and resource intensive. And therefore, here comes our research problem. What we have done is that we are implementing AI and machine learning models in order to predict such deformation without losing accuracy and in a fast manner. Going towards our introduction, let us understand what's behind auxetic sandwich panels. Sandwich panels are just a protective layer. What's unique about our system is that is the mechanical property of the sandwich panel, which is auxeticity, meaning that it has negative Poisson ratio, which behaves contrary to normal materials that expand, to normal materials that thin out when expanded, but auxetic sandwich panels expand when stretched in the lateral direction. So such benefits can be enhancing the energy absorbed by the sandwich panel, better indentation resistance for the sandwich panel, which is able to the ability to resist intrusion and improve deformation control. Going through the research aim, as we have discussed, we have developed a data-driven framework in order to predict the deformation in both of the components of our system, the auxetic core, which is the upper layer, and the layer beneath it, which is the underlying RC slab. And the contributions are we were able to replace the repeated FEA simulations, which took a lot of time. Actually, a year of our study was to simulate such scenarios of cases of impact scenarios, and to be able to replace such FEA models with machine learning models. And we were able to evaluate 3 categories of the machine learning regressor and show that machine learning can accurately predict the deformation. The contents are, okay, going through the overall framework, we can see here that these are the steps we have taken in the ANSYS program in order to come out with the outputs and the deformation. We were able to draw and define the geometry of both of the RC slab as well as the sandwich panel and assign all the parameters such as the height at which the impactor falls and the mass of the impactor. And then we were able to assign the boundary conditions to our system and run the simulations, which can cover a wide range of scenarios. Then we extracted the results. And which are the deformation in the sandwich panel and the deformation in the RC slab. Going through the machine learning models, we were able to extract and populate the data set we obtained from the FEA simulations and pre-process them and retrieve the features. Then we were able to split the data set into training and testing data set, which is a typical ratio 80:20, and train our models and do the evaluation in order to compare between them. The model setup, you can see here our model. We have a model just a quarter of our model, which is a typical approach or methodology adopted in many of the finite element simulations. In order to reduce the computational cost, we can see all the dimensions of our model here as well as the auxetic core dimensions. So in order to ensure that our model is behaving well and is repeatable, we must achieve a validation throughout in comparison or with the reference paper, which is an experimental model. We can see here that our numerical model achieved 99.57 the deformation millimeter versus the experimental model against the reference paper, which is 95.37 millimeters, just 4.41% difference. The dataset construction from the 90 simulations we have done over a year, we were able to come out with the outputs, and we were able to pre-process the data and train our models. These steps have been taken in order to train our models. We have tested 3 categories: the linear based models, the kernel based models, and the ensemble trees. Training and testing, we have done a 5 cross validation on our training data set. And these are the metrics we are comparing all the models with. Going through the exploratory data analysis, we can see the role of each of the pressure and the velocity on the core deformation. We can see that the prominent or the main contributor of the core deformation is the pressure, which has a steep trend, as we can see, as well as the velocity, which is not very dominant, such like the pressure, but it is doing impact also. We can see the correlation matrix here that the pressure is highly affecting the core deformation with a percentage of 89 in comparison to the velocity with a percentage of 0.22 only. Here we can see a 3D plot surface diagram showcasing what we just have said. Going through the core deformation model performance, we can see that the ensemble tree models achieved high accuracy and are showing good results, such as the extra trees and random forest are showing 98% and 97% accuracy, which means the model is fitting well. And the mean absolute error, we can see that the error for the ensemble trees is just 1.69 millimeters, which is not very high in terms of our application in the structural field domain. Going through the root mean square, which is able to detect or sensitive to high error, we can see that the highest is the lowest is the extra trees with just 2.40 millimeter error.
Sorry for interrupting. Just be aware of time. We
yes,
have like
I'm just about to conclude.
Yeah. Okay. Thank you.
So such approach was also implemented. We can see here the best fit line for all of our models, and we can see that the ensemble tree models, the dataset is just well aligned around the best fit line in opposition to the kernel ridge model. We have done the same approach for our slab deformation, and we can see just quite the opposite. So the models that performed well for predicting the core deformation performed actually the worst for prediction the slab deformation. And we can say that the mathematical nature of the algorithms, does not necessarily match the physical behavior of our model, of our system. So so we can say that the slab deformation is more global and smoother, while the core deformation is highly nonlinear, and therefore we can see that various models perform better in different components of our system. So interpreting our results, we can say that, as we have said, different layers have different behavior, and for the auxiliary core, it has a complex local mechanics with highly nonlinear behavior, which is best captured by the ensemble trees in opposition to the RC slab, which has a global deformation best captured by the kernel or linear models. We can see in both the core deformation and the slab deformation that the pressure is the dominant factor affecting the deformation. Okay, concluding our study, we have been able to prove that when finite element simulations are combined with machine learning tools, they are efficient in predicting our parameters, whatever they could be, such as we have shown that it has high predictive accuracy for both of our components in the system, which we were able to reduce the computational cost and time very well. This could provide a practical tool for early stage design, sensitivity studies, and potential near real-time impact assessment. As we'll see in our future work, we can deploy such a system, but in real time, up to the second, in real world, and we could further extend our work for a more complex material, such as foams or hybrid oxides, and different impactor shapes or boundary conditions. Thanks, and if there are any questions. I'd be happy to hear them. Thanks a lot.
Thank you, Bahi, for your presentation. You can see that you used machine learning in your civil engineering work.
Yeah.
Which we didn't understand anything from the civil engineering side.
I tried my best.
Yeah, we can see that you used a lot of machine learning.
We are just
did
talking
a lot
about
of
protective-
analysis
Yeah.
using machine learning, which is good. I want to ask you a civil engineering question.
Yes, sure.
What's slab and what's slab deformation that you are trying to predict?
So a slab is
the main core of your work.
A slab is just a structural component, such as the roof above us is a slab, or a wall is a reinforced concrete slab. Reinforced concrete slab. Yeah, it's just a reinforced concrete component, and in many cases we need to protect such systems, and therefore, in order to protect such systems, we need to put a layer of protective system in front of them. Yes. So in this case, we have put the sandwich panel with a special kind of mechanical meta material in order to protect the concrete or the building facade, or for example, a glass cladding or whatever it could be. And so we were able to save the time we could spend in simulating such simulations using the finite element analysis software by only generating a minimum data set and using such a data set to further predict other scenarios in our cases. With different velocities or height, the impact could be falling on the RC slab. Yeah,
Very
I tried my best.
interesting to see how
Thanks
you
a
are
lot.
using machine learning in your work.
Thanks.
So thank you. Do you have any questions? Thank you, Bahi.
Okay, thanks.
Yeah.
Yes.
Altair or any other software, because I believe in Altair we have this option. We have adding ML models so that we can speed up the things.
Within the software itself?
Yeah, it's a neat feature, I think.
I'm not really sure. Maybe it's a recent feature. But
Yeah, I think.
Yeah, so maybe I could further
It's worth looking.
search into that. Yeah.
Yeah.
Thank you for the question.
Great work, by the way.
Thanks a lot.
Thank you, Bahi.